Hello all, please join me in welcoming Jayson Grace and Aleksandar Straumann. Jayson is a penetration tester at Facebook, and Aleksandar is a security engineer at Sandia National Laboratories. Their talk, MOSE, Using Configuration Management for Evil, introduces a post-exploitation tool that uses configuration management servers to compromise associated agents.
Cool. All right, there's Al, that's good. All right, hello. Thank you all so much for hanging out and coming to watch our talk. Today we're going to be talking about MOSE, which is a tool to help you to use configuration management servers for post-exploitation. Any opinions that are expressed over the course of this talk are our opinions and don't reflect those of our employers, and all of the work that we've done has been as independent researchers and subsequently not associated with our employers. So my name's Jayson. I've been playing death metal for several years now. I used to tour, but now I just play local shows every so often. Of course, when there's not a global pandemic going on. I'm currently a member of the Red team at Facebook. Before that, I was a penetration tester on Splunk's product security team. And prior to that, I founded and led the corporate Red team at Sandia National Labs. And I really enjoy automating things. It's one of the pure joys that I have in this world, but I have a special place in my heart for automating post-exploitation tasks.
Hi, my name is Aleksandar Straumann. I mostly go by Al. Jayson, I don't think you're presenting the slides right now. I currently work as a security engineer at Sandia National Labs, where I work on various assessments, both penetration testing and more red team engagements, as well as tool development. And my passions strictly lie with kind of the tool development aspect, as it kind of helps me develop skills that I can use in my day-to-day. And MOSE was just one of those tools.
Cool. Slides look good?
Yep, all good.
Solid. All right, sorry about that, folks. On the agenda for today, we are going to begin by briefly discussing what configuration management tools are. Following that, we will discuss how attackers can take advantage of them. Once we understand that, we will then talk about what MOSE is and what we are hoping to accomplish with its creation, and there will be some demos.
So real quick, for those of you who are unaware of what configuration management tools are used for, they're used for maintaining and provisioning systems into an expected state. So the configuration management tools can also be used to manage the expected state of a machine. For example, if you want to make sure that a service is always running, software is installed on a machine, or you want to make sure that machines are automatically updated regularly on a scheduled basis.
And so the tools that are the most prominent on the market these days are Puppet, Chef, Salt, and Ansible. And if you haven't run into these yet, you certainly will. A ton of companies use one or more of these tools. And these tools have some things in common. For starters, they all have this concept of idempotency, meaning that you can run the code as many times as you want and expect to produce the same result. They also give you the means to scale infrastructure while guaranteeing consistency across it. You have the ability to provision machines that are running on a variety of operating systems. So you could have a Puppet module or a Chef Cookbook, Salt State, or Ansible Playbook that works on Red Hat, SUSE, Debian, Ubuntu, and Windows. And they all have a form of secrets management, which we'll get into a little bit later.
So while these tools are all used for the purpose of configuration management, their implementation will vary slightly from each other, and that might direct you to use one over the other. For instance, Puppet and Chef have agents which pull down changes from a centralized server, while Ansible and Salt will push their changes onto their managed nodes. The terminology will differ from each of the tools that you decide to use. Ansible further deviates from the paradigm by being agentless, which simply means that it uses another protocol for the authentication and management of its nodes, typically being SSH. So this also allows Ansible to apply configurations to any agent with the SSH key, so long as it has access to it. So there are some more differences, but ultimately it kind of comes down to preference and the environment which you want to work in and deploy them to. In short, they all solve the same problem, but their implementations vary, and it's up to you to make the decision on which one you want to use.
And so we're going to show you an example in a bit here of how provisioning a system works, but If you're still trying to figure out why you would use this technology, a prime example can be avoiding things like this 1100 line bash script, which has 0 functions in it and is completely void of hope for future generations to maintain. It's a great idea to have code driving your infrastructure and any changes that need to be made in it, but it needs to be modular, easy to test, and easy for others to pick up in the event that you're no longer in the picture. All right, so for this example, we are going to be looking at a Puppet managed environment. So we start out on the Puppet master, and we are going to look at the main manifest. In this particular example, we're going to be provisioning webprod.demo.com, but one thing that is worth noting in Puppet specifically is no default covers any cases that are not explicitly defined. However, for the example that we're doing, we are essentially going to be installing a web server and then running a web page on top of that web server. So as we can see, there is not anything running on port 80 currently, but let's go ahead and pop into that Puppet agent and check in with the Puppet master. So this is the managed node. As you can see, there is no web server running presently, but we'll go ahead and run Puppet agent -t. This will kick off checking in with the Puppet master, and the Puppet master will tell it that you have new instructions. You are going to install a web server and run a web page on top of it. And as you can see, we are now running a web server. Let's see if the web page is there. Looking good. Let's take a closer look. Once we get the public IP address from the metadata service. There we are. Cool. Looks like we have a web page running on top of a web server. So hopefully that gives you a sense of what this technology is used for. Now, a common question that comes up around this technology is, in this day and age, we have containers, we've got Kubernetes, like really, who needs this stuff? And to that, I would say a couple of things. First and foremost, not everything can be a cloud native ephemeral workload that runs in a container. Furthermore, it's typically not a trivial effort to migrate older monoliths to container-based deployments. And finally, you still have to install, configure, and manage your Kubernetes deployments with something. Ideally, something that's repeatable and can be tested regularly in an automated fashion. This is where configuration management tools can do quite well for you. A lot of companies, for example, will use Ansible to stand up and manage their Kubernetes deployments.
So from the previous video, you can kind of begin to get a sense of how powerful configuration management tools are. Unfortunately, or fortunately for us, they're incredible resources for attackers. We can abuse the tools that are meant to provision and maintain systems to introduce any commands or tools that we as an attacker kind of want access to. Any changes we introduce will be run on any of the systems that the specific configuration management server manages. And once compromised, we can do all sorts of things. It's essentially a shell in a box. So configuration management tools often operate on schedules, similar to a cron job. And this means that your introduced changes will persist so long as the initial vector of compromise is never found. And the impact of this is particularly devastating, as blue teams will oftentimes use configuration management tools to provision and maintain systems that their SIEM and source solutions operate on. So pwning the main configuration management server can effectively change what the blue team sees, resulting in complete compromise of the infrastructure. And further damaging is the ability to modify and introduce backdoors into production systems that may host company websites, production software, or even just development environments in general. And lastly, oftentimes you need credentials in order to set up systems in an environment. And so most configuration management tools have ways to store these credentials or secrets. And that means we can steal those secrets. So these credentials are created to run in an automated fashion, which means that their overall security is lessened. So stealing them can provide us as an attacker with many lateral and vertical escalation paths. A lot of the times, it's as easy as running a decrypt command to gain access to these credentials or secrets. However, you need to be careful when using them because they're automated. There's like this predefined behavior for using these secrets. Defenders can oftentimes build alerts around them and their expected behavior so they can quickly determine when they're being abused. So with that in mind, we can see how MOSE fits into all of this.
Yep. So MOSE is effectively a translator between a user and a variety of CM tools. The idea being that we know what commands or code we want to run on our targets, but we don't necessarily know how to implement them for a given CM tool. So MOSE takes the commands or code that you want to run on CM managed systems and translates them into a format that a given CM tool can understand. It also takes care of getting things into place for you as well, so that when the managed nodes check in with the server, they run whatever you've specified. It is written in Golang. I chose Golang because it has a few really useful features. First of all, it enables us to easily target a wide variety of operating systems and architectures. It also has native concurrency and allows us to generate a binary that can run on a target system without having to worry about dependencies. I would also venture to say that the fact that Go has these makes it a fantastic tool for OffSec tool development in general. So if you haven't popped into Go for a try, maybe give it a shot next time you're going to throw something down. MOSE is an open source tool that I came up with in December of 2018, and I released it and presented on it at DEF CON 27 in August of 2019. I also gave a talk at B-Sides SF earlier this year. For this talk, I'm incredibly excited to have Al join me. Al has been my contributor on the project for a while, and without all of his hard work, MOSE wouldn't be the tool that it is today. So far, we have a small team of core developers. You are looking at us, and we are always looking for contributors and testers. Right now, an event called Hacktoberfest is actually being put on by DigitalOcean. If you're not familiar, it happens every October, and basically you can sign up for the event, and if you create 4 pull requests during the month of October, you get a cool t-shirt and some awesome stickers. So if you have some great ideas for MOSE and you want to get some of your PRs knocked out, we'd love to have you join us in making this tool a staple in the security community. And so I was motivated to create MOSE for one main reason. Configuration management tools can be as difficult to exploit as they are powerful. One reason for this is that each CM tool has its own learning curve. If you check out the docs for any of these tools, you'll quickly see that there is a lot to digest. There are many tool-specific idiosyncrasies and gotchas that you need to be aware of before using them. They also have significant differences in their workflows, syntax, and architectures. And since you'll likely encounter several different CM tools while on engagements or at different jobs, you'll have to deal with this learning curve multiple times over. Ultimately, you can't choose which tools your target uses, so you want to be able to weaponize them all and not have to worry about tool-specific differences. It's also important to keep in mind that with great power comes great responsibility. You can break a ton of systems while attempting to backdoor a CM server if you're not careful. Imagine changing a couple of lines in a file and saving it off, and before even a minute, a bunch of production systems are knocked off, hundreds potentially. If that's not in scope for your engagement, which let's be frank, it isn't for any of us, you're probably going to be in a world of hurt. And to give you some perspective, these are some of the links that comprise the documentation for Puppet. This is what I'm talking about with respect to the learning curves. The documentation for most of this technology is extensive and takes time to ingest and understand. And as someone who has done this manually several times before creating MOSE, I thought it would be helpful to outline the process for you. First, So to start, we will have to figure out how the CM server is configured. And fair warning, a lot of the implementations of these tools that I've seen lack uniformity in how they do things, as apparently best practices are merely a suggestion for a lot of organizations. So you'll need to figure out how they've done their deployment before you can get to the good stuff. This typically involves a lot of guessing and going down various rabbit holes, which can get to be time-consuming and torturous, especially if you're time-boxed on an engagement. Next, you need to figure out where your backdoored code needs to go. And depending on how the environment is configured, this could be in a number of different places. Next, you need to find the right files to reference your code in. And once you found those files, you'll need to make changes to them in order to hit whatever hosts you're targeting. This is the part where you got to make sure that you don't break anything and or everything in that environment. And once this is all done, you'll need to figure out where the secrets are stored and how to decrypt them, which of course this method varies for every CM tool.
So that's a huge pain. And MOSE is here to automate all of that for you, which is a huge time saver. We've also added some quality of life improvements that allow you to be more strategic in which nodes you want to target or specific tasks that you may want to target, such as you only want to target web servers for uploading a web shell or stealing all AWS keys from the managed EC2 instances, or just simply limiting your presence during an engagement. So because MOSE allows you to be pretty accurate from discovery to the exploitation phase without kind of having to go deep into the weeds of tool specific details, it kind of helps to prevent someone who's less experienced with any one of these details from just breaking everything, as Jayson's already mentioned. So it really kind of empowers you to focus on what you know and to not have to get wrapped up in the little details of each technology. And so MOSE is great for everyone. You don't have to know tool-specific implementation details to run MOSE either. Commands are input the same way for all supported configuration management tools, and there's even granularity if desired. More experienced users can modify the templates that we utilize for basic payload generation to create something much more curated to a specific task or tool that they have in mind. So with that, let's see kind of a basic workflow for working with MOSE.
Yep. So this is the workflow for using MOSE. Essentially, in this particular instance, we're going to be targeting a chef environment, and we've specified that we want to create a file and then throw a string into it. Not super exciting, but easy enough to understand for an example. So once you run this command, MOSE will generate your payload for you as a binary. And then by default, it will host that payload for you with a web server that it stands up. Alternatively, if you don't want to go this route for transferring your payload, you can use another command line parameter to just spit the binary out to disk, and then you can get it to your target whatever way you choose, whether that's SCP or what have you. Once your payload is onto the target system, you go ahead and run it, and it will start by identifying things like the managed nodes and potentially things like the cookbooks that are in place for that environment. It will then ask you if you want to make backups of the files you're going to modify, which is a good idea, unless you're trying to be stealthy. Following that, it will ask you if you want to target specific nodes or everything in that environment. And once you answer those questions, you're off to the races. MOSE will introduce your backdoor logic and then try to pillage any secrets it comes across.
Cool. So let's see how that looks in practice with MOSE versus Ansible. So real quick background for how Ansible kind of functions. At bare minimum, you need a playbook, which is going to contain a list of tasks or commands that you want to push off to the managed nodes. The inventory is going to contain a list of the host machines, the managed nodes in this case, that you want to apply your specific changes to. So from there, we can use MOSE to inject into a playbook. As you can see here, we execute MOSE, we specify the configuration management tool, in this case Ansible, and the payload that we would like to inject into our maliciously introduced role. In this case, we're just going to echo some contents into a file, and then there's an additional flag there that just allows me to specify which interface I want to bind on for our demo. So we serve it up on a local web server, and after that, we wget it from the control node. See there, easy. And the next step, we execute it. So it's going to run through all the steps that Jayson just mentioned, identifying the systems. It's going to ask you some questions for backup, and it's going to go through some more granular options. In this case, we only have one task because it's a very, very simple playbook. And so we inject into that. And then it finally dumps the secrets, or secret in this case. So to see if our injection was successful, we can execute it now. Oftentimes, Ansible is automated either using cron jobs or Ansible Tower or Jenkins or what have you. And in this case, we're just going to manually kick it off for the demo. So we take the Ansible playbook command and specify the site.yaml that we've injected into. And you can see that the malicious role, my command, has been injected into the site.yaml and executed against the control node. So just to see that that's worked, we'll go on to the managed node. And you can see that our file has been created with the contents that we want on the machine.
Cool. Let's go ahead and take a look at MOSE and Chef. So Chef has two components that can be compromised. You have the Chef workstation and you have the Chef server. The Chef workstation is usually run from a developer's laptop, a dev group server, Jenkins, etc. And as far as Chef nomenclature goes, basically Chef nodes run a client, which is known as the agent. So I will probably use agent and client interchangeably, but rest assured they are the same. Alrighty, so compromising a workstation is a bit more straightforward, so we'll cover that first. Similarly to what we did with the Ansible environment, we specify the CM tool that we're targeting, the command that we want to run on the managed nodes, and then we hit enter. This will, again, by default, cause MOSE to serve our payload with a web server that it stands up for us. Go ahead and download that payload onto our target Chef workstation. And then when we run it, a couple of things happen. First and foremost, as mentioned previously, it identifies the agents that are being managed by the Chef server. It also identifies the cookbooks that are in place for that particular Chef server, which can be useful to get some context for the environment and get a better understanding of what it is you're looking at. Next, it asks us if we want to target specific Chef agents. In this particular case, we are opting to target Chef Agent 1. Once we go ahead and hit enter there, it will create the cookbook for us. And then when that agent checks in with the Chef server, by default, every 20 minutes with the Chef client cookbook, which is considered an industry best practice, our backdoored logic will be run. And of course, there is a secret that we can go ahead and hold on to for later. So we wait for 20 minutes, or we go ahead and check in manually so we can get this nice screenshot for all of you to kind of see what's going on. And as you can see, it synchronizes the cookbooks that are associated with its run list, and it finds that it does need to do something for this my command, which is a new cookbook, and subsequently it executes the logic that we specified through MOSE. That was pretty easy, right? Pretty simple, similar to what we did with Ansible, really. But landing on a Chef server is a bit more complicated than that, unfortunately. It makes me need to drink every time I think about it. So as a quick point of reference, we've landed here, and the Chef server is connected to Chef agents. So we can spawn a cookbook with MOSE, but Chef server has no way to provision Chef agents. So we need a Chef workstation. What we can get from the Chef server are the certificates and organizations that are in use in that particular Chef environment, which can be used in conjunction with a Chef workstation to achieve our desired result of running our rogue cookbook on the Chef agents. Now, we don't want to install workstation on the Chef server because we could potentially clobber some dependencies, or just doing that could just get us caught anyway. And we don't really want to have to install it on our system either. And in an ideal world, it would be great if it was automated for us so we didn't have to think too hard about it. To solve this problem, we have leveraged Docker and some templating. And so the idea is we exfil all the data that we need and use it to automatically build our own Chef workstation. So to visually sum up what the plan of attack is here, we land on the Chef server, exfil the keys and org names to our system, which we then use to stand up our own Chef workstation with Docker. And then we can use that to go to town on the agents that are managed by the Chef server. Let's go ahead and walk through that. So this command is obviously pretty similar to the one that we did for the workstation, with the exception of this -L here that allows us to say that this is our local IP address. That will come in play. That will be useful for when we need to pillage the secrets or the org names and the certificates. We're opting to use TLS, and then this parameter here will basically throw the Chef server's host name and IP address into the etc host file for the container that we stand up. So we go ahead and download our payload. You'll notice that we provide a self-signed certificate with MOSE, which I highly recommend that none of you use. And if you do use it, I hope that you get popped by the blue team. Once we go ahead and run MOSE, it determines that we are on a Chef server. Back on the attacker system, as soon as we download the payload, we are asked a couple of questions. First off, are we on a Chef workstation? We are not. We are on a Chef server. And when we say that we are on a Chef server, it will stand up our listener that we can use to exfil the stuff that we need. So let's move on to exfil. It's pretty simple, really. MOSE finds the stuff that we need to steal and sends it to the endpoint that we stood up. And so now that we have the information that we need, we can stand up a workstation of our own and use it to run the command that we wanted to run initially on whichever managed nodes we choose. And so MOSE stands up a container for us with all of the dependencies that we need, and it then drops us into it. So at this point, you are really just going to follow the exact same steps that you would as if you had landed on a Chef workstation in the first place. Cool. At this point, we are on to the demo portion. So this is a scenario that I ran into at some point in my career. We are going to compromise a Chef workstation and leverage it for lateral movement and persistence with the help of MOSE. All right, so we do some recon and we don't find any vulns on their externally facing web application, but we do some port scanning. We find port 2375 is exposed to the internet, which is handy. That is the port for the Docker socket. And so what we could do there is we could create our own container and then mount the underlying file system for the host into that container, which is exactly what we're going to do. Cool. At this point, we are in that container. And looking around a bit, we see that there's a public-private key pair. That's cool. Take a look at the private key pair. It's not encrypted, which is helpful. Although we don't really know what it goes to, so we'll have to do a little bit more digging to see if there's anything we can do with it. Fortunately, after a bit more digging around, we see that in the bash history, there is a command that helps us to use that certificate. So we'll go ahead and test that out and see how it works. Neat. At this point, we are on a Chef workstation. I've skipped a lot of the steps that you would do for discovery and kind of getting a better sense of where you are, but rest assured, we are on a Chef workstation that is managing some agents. So we're gonna look at taking advantage of those. To start, we are going to kick up a reverse shell payload and use that to access one of the systems that is managed. This is just a Python reverse shell, pretty textbook stuff. So we specified that reverse shell script that I just showed you. And at this point, we are hosting the payload. We go over to the compromised Chef workstation. And we can go ahead and grab that. Once we've got the payload, we go ahead and extract what's in that tar file. If you do a shell script with MOSE, you got to extract stuff out of a tar file, but that's all right. So as you can see, a couple of nodes were identified. Also, we see that the cookbooks that are in place already were identified. We're opting to target the dev system. And so as you can see, there is a cookbook now that will run our reverse shell on the dev system. And it looks like we also got a secret there, so we can hold on to that for later and see if it does anything for us. So now we got to wait for 20 minutes for the agent to check in with the server and introduce our logic. But fortunately, through the power of video editing, we can just set up a listener and then magically a reverse shell appears. It's great. So at this point, we are on the dev system, which is one of the managed nodes for that particular Chef server that workstation is interfacing with. A couple of interesting things off the bat. Permit root login is allowed for the SSH config. And we kind of figured that out already, but this is helpful because it's a CM managed environment. That's probably a policy that's in place for all the systems, so we can take advantage of that. It also looks like there is a MariaDB system that is known to this host, so we can test out that secret and see if it is a fit. Cool. So we can come back to that database later and pillage it. And so if you were paying attention, we also saw that there was a web server that is being managed through that Chef server. So we're going to go ahead and take advantage of that now. So we'll throw a web shell up, and then we will weaponize the www data user. So pretty similar to what we did with the reverse shell, we specify the bash script that I just showed you for the payload. At this point, we are hosting the payload. And so we can go over to the workstation, download the payload, extract it, and run it. For some reason, when I was filming this, I kept wanting to rename files.tar.1 to files.tar. I don't really know why, but I did it. All right, so we're running this payload, and this time we are going to target the web server. Cool. So at this point, that should be in place for our web server when it checks in with the Chef server. So now we can go over to the web server, and let's say for this example that it is a publicly facing one. So pop over to that real quick. There we are. And we can go ahead and check out the endpoint where our web shell should show up. Currently, as you can see, there is indeed nothing to see here. But when we wait for 20 minutes or through the power of video editing, we now have our web shell. So just looking around a bit, checking out what processes are running. Looks like the www data user is going to be a great guest for us when we did our set action earlier. And if we look at the hosts, we can see that this system also is hooked up with the dev system, which we have a reverse shell to currently, and the workstation, which is what we compromised through that initial vulnerability. So we should figure out a way so that if we get kicked off of our reverse shell and that initial vulnerability gets patched, that we can get back in. So what we're going to do is we're going to spawn a rogue SSH key pair. And of course, because we currently have shells to those two systems, we could just knock those in manually, but blue team comes and finds those and gets rid of them, we're SOL. So we can go ahead and use the Chef server to do that for us so that even if they remove that stuff, it'll come back. And in my experience, blue team isn't as keen on knowing to look for these sorts of things in the configuration management servers. So this is a nice persistence mechanism that'll probably let us hang out for a little bit if we're not too noisy. At this point, we're knocking our persistent script in that will get our pub key in place for both the dev system and the web server. Go ahead and run it. This time we're targeting the Chef workstation and the dev system. Very nice. So at this point, let's say that we lost our initial means to exploit that system with the Docker vuln, and the blue team has also killed our reverse shell and gotten rid of our web shell as well. So we, at this point, need to wait for the agents to check in with the server and get back in. So we'll set up a listener and we'll come back. The web shell's back. We can use that to send off a reverse shell to our listener. And at this point, through that persistent script that we did, we should be able to SSH right back into both the dev system and the Chef workstation. So hopefully this gives you a sense of how you can start to leverage configuration management servers for post-exploitation. If you end up using this on an op or an engagement, I'd love to hear about it. And obviously with not too many details, but just to get a sense of what you've done and some of the successes that you see. All right.
Awesome. So I have one more demonstration for you. And in this scenario, we're going to be leveraging a compromised developer machine where we've already done the due diligence to kind of do our privilege escalation as well as some post-exploitation. And in this scenario, we know that the demo man user has used Ansible Tower to provision systems across the infrastructure, but there is no Ansible on the system that we can use to connect to other systems inside of the infrastructure. There is an SSH key. However, it doesn't allow us any access for lateral movement via SSH. So with that in mind, we can move on to the demo. So we're going to start out on the victim machine, the developer's box, and we're going to list out the contents of the home directory. We're going to notice a weird file, this tower CLI config, and tower CLI is a way for connecting to a tower instance and executing commands via the command line. However, unfortunately, it stores the credentials in plain text if you're not careful. So we're going to take those credentials and we're going to log into the tower instance. From here, we're just going to poke around a bit. We're going to notice that there's only 2 users on the system, the demo man user as well as the admin. And we're only able to access the red organization. And there's 1 project. And the project uses a Git repository, the MOSE-demo.git, and it's set to update on launch, which is important for what we're going to do. The template uses that project and specifies a site.yaml and some extra variables when launching. Unfortunately, we can't edit anything as we only have the ability to execute with the current permissions we have. So we're going to go back to the developer machine and just poke around a little bit more. So within the working directory, we're going to notice that the site.yaml exists here and that there is a .git folder. And so we're going to want to check if that repository that's on the developer's machine points to the same remote. In this case, it does. So we can use MOSE to attack this. So from our attacker machine, we're going to generate a payload using some bad keys that we've generated. And we're just going to generate a simple payload that cats the contents of that public key into the authorized key files of the root user. And we're going to SCP this up. Now, one of the reasons this works is that developers will oftentimes use passwordless SSH keys to gain access to Git repositories without really thinking about the consequences of anybody who might stumble across this maliciously. And that's the case that I've seen a lot of, as well as Jayson. And so back to the developer machine, we're going to cat out the contents of that site.yaml. There's a conditional flag and an import playbook for the basic prov. So that's going to be the target for our attack. So we sudo su to the root user that we've compromised, and we're going to go to the home directory and execute our payload. So from here, we're going to specify the roles directory as well as the playbook that we specifically want to inject. Because Ansible isn't actually used on this system, the ansible.cfg is not going to exist. So we're going to create a backup, and we're going to target all of the tasks within that basic playbook. And so back to the demo man user, you'll notice that the backup file exists. And within the source control, we're just going to do a quick git diff, and you'll notice that our malicious role, the mycmd, has been injected. You can always change this to your preference. So we'll add that to source control. And we're going to cat out the contents of our malicious role to make sure that everything looks kosher, and it does. So we'll add that to source control. We're going to put an innocuous commit message for the case that the user doesn't have privileges to force push. So that way, no one would really bat an eye at it. We'll push this up to the master branch. And then we will sudo su back to the root user and do some basic cleanup. We're going to specify the -c flag as well as the playbook that we injected into so that our payload knows which backup file it needs to replace the contents of. So we're just going to say, yes, please clean up everything. We're going to get rid of that Ansible binary. And we're going to switch back to the user, make sure everything looks good. So the backup file no longer exists, as well as our malicious role file. So later, we can do just some more covering of our tracks. Onto the Ansible Tower instance, we have the ability to execute. And since the project is set up to allow update on launch, we can kick off this job. And the basic flag for the environment variables or the extra variables allows us to specify which imported playbook we want to kick off. So we specify basic to true, and we launch our job. So this is going to be sped up, but you'll notice some yellow text flyby, and that means our task has likely been kicked off. So to test this, from the attacker machine, we're going to use our maliciously generated SSH keys, and we're going to use the demo man's box as a proxy for our SSH tunnel. We're going to use one of the IPs from the change task command, and we're going to try to SSH into it. And hopefully this will allow us to gain access as the root user. Takes a couple seconds because we're proxying, and there you go. We now have root compromise of all the managed nodes.
Very nice. So I bet after those sterling demos that you all are ready to test out MOSE and see what it can do for you. One thing that is always kind of a bummer for me whenever a neat new OffSec tool comes out is it comes out to solve a problem, but you don't really have anywhere to try it out. And so you forget about it, and maybe by the time you actually find a problem where you could use that tool, you've forgotten about it. For us, we decided that we wanted to have test environments for every single one of the CM tools that we've mentioned throughout the course of this talk so that you can just go out and try MOSE immediately. There are clear instructions on how to build and run them for each repo in GitHub. They're pretty much all Docker-based, so pretty easy to stand up, really just make run. One of them is Vagrant-based, but again, we've abstracted a lot of the work just with a make command. And you can actually do the demo I showed previously yourself. It can be found in the Chef Test Lab repo. And also, if you happen to watch the DEF CON version of this talk and want to reproduce those demos, you can find those in the Puppet Test Lab repo. And for any forward-thinking blue teamers out there, I'm a big advocate for having blue teams adapt red team tooling in order to better their defenses and knock out some SIG-gen, ultimately with the intention of detecting low-hanging fruit. So if you're interested, again, I think MOSE with the test labs could be useful for that purpose.
So when Jayson first introduced this tool, we only supported Puppet and Chef. And we've now been able to support all the tools that we kind of sought to support when MOSE was first started. So that includes Puppet, Chef, Salt, and Ansible, for those of you that may have forgotten. And we really just want to kind of push the importance that MOSE is open source, and we really would like contributions. Any feedback, contributions always make tools better. So if you think we could have done something better, give us some feedback, give us a pull request. We'd love to see some alternate diverse opinions.
Yeah, get that cool t-shirt and stickers.
Yeah, and just a quick plug, Sandy is hiring for the red team that I work on. If you're interested, please reach out to me at the following email address.
Yeah, and as someone who spent most of their career in the DOE space and started that red team, I can confirm that is a fantastic place to work with some great people. Highly recommend it. Real quick, I would like to thank my wife, Amanda, who is endlessly supportive and patient with me. I'd also like to thank the B-Sides Boulder staff for rolling with the punches with this whole pandemic we're all going through. I'm really hoping to move to Denver in the near future, and I was very excited to be a part of this conference and get to network with some of the great folks involved with the security community there. So I'd love to keep in touch and hear about how everything's going in that neck of the woods.
Yeah, and I just want to thank my mom and dad, Bridget and Travis, and my girlfriend, Aishwarya, who have put up with me ghosting them for the entirety of this pandemic as I've been working on this project with Jayson. And I also want to thank the B-Side staff. They've done a really good job, and I know this must be incredibly stressful, but they've pulled it off, and it's gone really well from what I've been able to tell. So thanks again, and it's been a real pleasure.
Absolutely. Again, I'm sure you all have some great ideas on how to make MOSE better. Luckily, it's open source and it's Hacktoberfest, so contribute your ideas, get them stickers in that cool t-shirt. This is where you'll be able to find MOSE and the associated test labs. And with that, I will be catching up on questions in the Discord, and something else will happen, I imagine, through Matt.